Hi everyone! Today we're looking at elastic potential energy. As always, pause the video, find yourself a quiet space to work in. You're going to need pen, paper and a calculator for today's lesson, so please make sure you have a calculator ready to go. Alright, once you've got that sorted, please write down your LO and today's date. So, like always, let's start with our retrieval. Pause the video now and give yourself a few minutes to complete this. Okay, let's go through the answers. So, what is kinetic energy? It is the energy stored in a moving object. Remember, kinetic energy is to do with anything moving. What's the equation for this? It's EK is equal to half times mass times velocity squared. Or if we want to write it as symbols, EK is 0.5 mv squared. What's a system? It is an object or a group of objects. What is the equation for work done? Work done is force times distance, or again, if we want to write it in symbols, W equals F multiplied by S. And then the last one, a car with a mass of 700 kg is moving with a speed of 20 meters per second. Calculate the kinetic energy of the car. So your EK is equal to half times mv squared. Pop in your figures, so we've 700 for our mass and we've 20 for our velocity. Pop all of that into the calculator, not forgetting to square only the 20, and we get 140,000 joules. If we convert that, we can convert that to 140 kilojoules. Okay, so remember that K just means multiplied by 1,000. Alright, so here is what the specification asks us. If you'd like to pause the video now and have a read through what the examiner is going to be looking for you to know. So what we're looking at today is we want to be able to describe what is elastic potential energy, and we want to be able to calculate that in a stored stretched spring. Okay, so looking at these two objects, what have they got in common? We've got a toy and we've got a grandfather clock. What is in common? So hopefully you knew that both these objects actually both have a spring. So now that you know they both have a spring, what does that make you think they might have? Well done. They both have elastic potential energy. So anything with a spring has elastic potential energy. And that leads us on to this diagram here. So what happens in a spring? A static spring just means a spring that is sitting on your table. So if you get a slinky, I'm sure loads of you have used them before. You might have had them as toys when you were smaller. And if you got that slinky and you pressed it really tightly between your two hands, you could make it smaller than it is. If you then caught it and you applied all the force you could and stretched it out as wide as you could, that's stretching the spring. So the spring can basically do two things. It can be compressed or it can be stretched. In both of these things, we're basically applying force to the spring. We're applying force when we push it in really tight and compress it, and we're applying force when we pull it out and stretch it. What happens if I let go of the spring? Well, hopefully the spring returns to its original shape. And that means that a stretched spring is storing elastic potential energy. So if I stretch a spring, I know that I'm applying a force to it because I'm changing the length of the spring. And we know that work is applying a force to anything that changes its length or its direction or its distance even, sorry, not direction, it's distance. So a force applied to anything is work done. So if I put energy into that stretched spring, as soon as I let go, that energy that I've put in is going to change, isn't it? It's going to convert into possibly kinetic energy if the spring moves back in towards its original shape. So as I'm holding that spring, as I've it stretched or as I've it compressed, that spring is storing elastic potential energy. So you might want to pause the video and write down your definition, that a stretched spring is a store of elastic potential energy. Okay, can you think of any more examples where you might use elastic potential energy? So I've told you about grandfather clock. We use it in some toys. We also use it in springs. Where else might you have an example? Okay, so if I don't do anything to my spring, then my spring doesn't extend, it doesn't compress, it doesn't move. So this picture here shows you that there's no force applied to this spring, and therefore there's no extension. That's its original length. However, if I put a weight on it, so you can see here my little blue box represents a weight of 10 newtons. All of a sudden my spring is stretched. So my spring has elongated, it has extended due to the force applied to it. Due to that weight being added to it, its length has now extended. That means that spring is storing elastic potential energy. So we know, due to Hooke's law, that if I apply more and more force, then the longer my spring will get. So I can say that this is a directly proportional relationship. And all that means is that the more force I add to this spring, the longer the spring gets. And we get a lovely looking straight line graph going straight through the origin when we do this. So the more force I apply, the longer my spring gets. And this is what I call Hooke's law. Now, we all know, because most of us have played with springs or slinkies, and we know that sometimes if we stretch it that little bit too far, it doesn't return to its original shape. And that's called the limit of proportionality. Once a spring is stretched too far and no longer returns to its original shape, that means that it has reached its limit of proportionality and it's no longer a directly proportional relationship. Okay, and like I said, this is referring to Hooke's law. Now you will look at Hooke's law in a little bit more detail when you study forces, but just to have that idea in your head and to know that the more force we apply, the longer the spring gets until we reach its limit, okay? And we call that the limit of proportionality because it will not go back to its original shape. So hopefully now you've got a good idea of what elastic potential energy is, and we're going to now try and calculate it. So we calculate elastic potential energy using this equation. And this equation is actually given to us in the exam. We just need to know how to rearrange it. So the equation for elastic potential energy is EE is equal to a half multiplied by the spring constant multiplied by extension squared. Now, in the same way that we squared only the velocity when we talked about kinetic energy, we only square the extension in this equation. Okay, so when you pop it in your calculator, it'd be a good idea to say 0.5 multiplied by whatever your spring constant is, multiplied by bracket extension, close bracket, squared. Okay, just to make sure that you do get the right answer. If in the exam you make a mistake, as long as you've shown your workings out, you will get some marks. But please make sure, just note down the bottom that the spring constant is different depending on the spring we're using, and extension must be measured in meters. So if you're given centimeters or kilometers, you must convert it back to meters. So if you want to write down that equation, we are going to use it in some of the questions now. Alright, so I'm just going to let you pause the video here if you want to use the triangle to rearrange your equation. If not, again, just pause the video and rearrange it. So rearrange the equation so that you're able to find extension by itself and you're able to find spring constant by itself. So you might need to just give yourself a minute to do that. Okay, so hopefully you came up with the following equations. So the spring constant, so again, if I use my triangle, cover over my K, that's elastic potential energy divided by a half multiplied by extension squared. So elastic potential energy divided by a half times extension squared. If I want to find my extension, then I need to first find the extension squared, which is equal to elastic potential energy divided by a half times spring constant. And then to get the extension on its own, I know to get rid of a square, I square root both sides. That gives me the square root of elastic potential energy divided by a half times K. Again, this is why it's so important to recognize that square, because if we don't square our answer, we will not be correct. Okay, so we're just going to go through a few examples. So this is a sample one that we'll go through together. A spring has an extension of 20 centimeters. Calculate the elastic potential energy stored in the spring if the spring constant is 100 newtons per meter. So first thing we do is we write down our equation. So elastic potential energy is a half times spring constant times extension squared. And then we have to look at our units. So we've been given 20 centimeters. Remember, extension has to be in meters. So we convert that 20 centimeters into 0.2 meters. Pop all of it into the calculator. So that's a half times 100 times 0.2 squared. Make sure you square the 0.2. And that gives me the elastic potential energy of 2 joules. Okay, I'd like you to try this one by yourself. So pause the video now and try this one. Okay, so you've been given your equation. First off, we need to calculate the actual extension, don't we? How much was the spring compressed by? So we started at 50 centimeters and we went 30 centimeters. So we need to work out the compression. First, we need to change those centimeters into meters. So that's 50 centimeters, 0.5 meters, minus 30 centimeters, 0.3 meters, and that gives me 0.2 meters. Okay, so that 0.5 is your 50 centimeters converted into meters, and your 30 centimeters is 0.3 in meters. Pop all of that into the equation, so that's a half times 25, because that was given to us in the question, times 0.2 squared, and everything into the calculator, and we get 0.5 joules. Alright, so try this one. Remember, work done is equal to your total energy. Alright, so hopefully you realize that work done is equal to energy, so that means that 1 joule is going to be my elastic potential energy. So first off, I rearrange my equation. So the extension squared is equal to elastic potential energy divided by a half times K. Don't forget I square root it so that, and then substitute in all my numbers. So my energy, we said, was 1 joule divided by 0.5 multiplied by 50, because that was the spring constant. So my extension is 0.2 meters. However, they ask me, how long is it now? So if the original length was 20 centimeters, so add the extension to the 20 centimeters, and I'm going to convert that centimeters back into meters first. So that's 0.2 plus 0.2. My total length is 0.4 meters. Okay, so hopefully now you can use the equation to calculate the elastic potential energy. Here are just a few websites that are quite helpful. So you've got Free Science Lesson, BBC Bite Size, and Pass My Exams, and they all have helpful links for elastic potential energy. Next lesson is going to be on gravitational potential energy, and if you need any help, just drop us an email. Have a good day, guys.